So here we talk about the capacitor with a dielectric. Dielectric is a specific type of material so that it can change the characteristic of a capacitor. Okay, so here we can see two simple experiment. Okay, so the left hand side, okay, we have a battery. Okay, we have a battery. Of course, of course, it should be somehow connected like this. Okay, yeah. So actually, for the left one, okay, for the left subfigure, okay, we have this one. Okay, let's say the voltage or the potential difference is V. Okay, so we have also V here, and then something like this. Okay, so the comparing to this one, we try to plug in the dielectric. Okay, so this is the dielectric. In Chinese, this is called 电介子. 介子. Okay, dielectric. Okay, so we try to put something between the capacitor. Okay, like a sandwich. Okay, so this. Okay, so of course we don't change the battery. Okay, so the potential difference wouldn't change. The potential difference wouldn't change. And then actually we find that the charge here increase. Okay, the charge here increase. So for the charge increase, what kind of things change? Okay, so of course for a capacitor, Q equals CV. Okay, here V remain the same. Okay, V remain the same, and then Q increase, which means that C increase. Okay, what we get is C increase. Okay, for the other one here, like, so first of all we try to charge the capacitor. Q equals CV here. Okay, Q equals CV here. This is Q plus Q negative Q, and then V. Okay, something like this. Yeah, and then we try to disconnect the battery. Okay, after disconnect the battery, okay, so originally the capacitor is like hanging. Okay, it's like hanging, floating. Okay, so the charge cannot move out or any charge cannot move in. So the Q remain the same. Okay, Q remain the same. So here at this stage, we try to see, okay, how many, what is the voltage or what is the potential difference across the capacitor. Yeah, of course, when you try to, I would say if you do this practically, okay, that will be current, okay, driving out the charge, okay. So practically, I don't think it will work, okay. But the idea here is like, okay, so if you try to very quickly to measure the charge here, or measure the potential difference here, okay, the V will be something like this. So you disconnect again and then try to also plug in the dielectric, and then you also try to measure the voltage quick again. Okay, so you will find that, okay, of course we assume that the charge amount doesn't change. Okay, but we find that the voltage or the potential difference is smaller. Okay, so what it means is that here we also have Q equals CV for this case. Here we make Q to be a constant. Okay, we assume there is no charge can go in, go out. Okay, here V becomes smaller. Okay, V becomes smaller. Okay, according to the observation. So also we get that C is increased. Okay, so based on these two operations, okay, we find that C increase after inserting the dielectric inside the capacitor. Okay, So here we slightly talk about some hardcore physics here. So what is the dielectric? Okay, so dielectric can be like it has quite a lot of dipole, yeah. But the idea here is if the dielectric is just placed at a place that has no external E field, then all these dipole will be randomly oriented. Okay, so they just point to a different direction. Okay, so they just tends to yeah, of course. Actually, you learned the electric dipole in chapter 22. You know that the electric dipole can also generate E field, but here, if you don't have any external E field, they will be like randomly oriented, random orientation. Okay, in the absence of an external E field. OK， 在没有外部 E field 的情况之下，它们就会随机的朝向。OK, and then the E field they generate will tends to be cancel out. Okay, so they tends to be generate no E field. Okay, but here if you try to give it some E field, okay, if you provide some E field to it, all this dipole, okay, all this dipole will tends to point to the same direction. It's just like in the classroom. Okay, if it's not in class, so all of you may not be facing the screen. Okay, maybe you will just turn around. Maybe you just walk in, walk out. Even though during the class, maybe some of you will walk in, walk out. But actually, if it is not in class, you are more freely to maybe or just turn around to talk with your friends or do whatever you like. But during the class, it will be more tentative to that. During the class, maybe most of you will be facing the screen. Okay, so it's like having the class is like an external E field. Okay, and then you will be oriented to the screen. It is something like the dielectric. Okay, if you don't provide any external E field to it, they will be like randomly oriented. But if you provide some external E field to it, then they will be like orient to the same direction. Okay, it's like these two are the parallel plate. Okay, are the parallel plate. So if you provide some potential difference to it, and it will generate constant E field pointing to the right side. Okay, so in that case, the dipole in the dielectric will all align pointing to the right side, and in that case, this dipole, this dipole will also generate some E prime. Okay, so this graph is like this E0 is the external E field. Okay, this E prime is generate by the dielectric. Okay, so this is the total. Okay, this is the total E field. Okay. Okay, so it will be like always cancel part of the external E field. Yeah, because the idea is here is like, yeah, if you provide an external E field pointing to the right side, this means that all the positive end, positive side will go to the right side, and the negative side goes to the points to the left side. Okay, in that case, it will be more like a little bit positive. on the right side, and then a little bit negative on the right on the left side. Okay, yeah. So if you just consider the inner part of the dielectric part, okay, so you will feel like okay more. Okay, so the blue, okay, the blue color are the positive charge, and then the orange color is the negative charge. Okay, so even though okay, so the it is only a bit different. Okay, but it tends to be a bit more positive charge on the right side and a little bit more negative charge on the left side. So in that case, the dielectric itself with this alignment will generate the E field pointing to the left side, cancel part of the external E field. It always cancel part of the E field, not generate more E field than the external. Okay, so it will be always like a cancel part of the E field, making the total E field inside the dielectric smaller than the external E field. Okay, so what will it change the capacitor, or how does it change the capacitor, or how does it change the Gauss law or the Maxwell equation? Okay, so here is the idea is inserting a dielectric into a capacitor cause induced charge to appear on the face of the dielectric, weaken the E field between the plate. The induced charge is less than the free charge on the plate. Okay, so here what we do is actually like okay, originally Maxwell equation is like epsilon naught integration of E dot dA equals Q. Okay, so here what we have is we have this kappa here. Okay, this is a Greek letter. Okay, kappa, not K. Okay. Okay, so yeah, although they look alike, but yeah, this is kappa, not K. Yeah. Anyway, so okay, so we will add this kappa with the dielectric occurs. Yeah. Yeah. So actually, in some of the other EM material or EM textbook, they will use another variable called D. Okay, D will be like epsilon naught KE. Okay, to represent D, so that the Maxwell equation will be simplified as this. Or sometimes they will use another variable like maybe ER to be or actually E. Okay, I mean. E will be kappa epsilon naught, okay, so that it sometimes will also change the Maxwell equation to be like integration of E epsilon naught E dot dA, okay, equals Q. Okay, and for this case, we will put this epsilon naught inside the integration side because the material may not be so uniformly distributed. Okay, so this is the case. Yeah. Yeah. And okay, so here for this capacitor, okay, originally we don't have any dielectric. Okay, so this is just like what we have for the chapter 23. Okay, so we just assume a Gaussian surface, just including the bottom part of the top plate, and then also the inner part of the capacitor. Okay, so that only this surface contribute to the surface integral. Yeah, but here we try to make it something like like this. Okay, so so generally it will look like this, and then we will barely have the same Gaussian surface, and also this would be the yeah, this would also be the only part contribute to the surface integral. Yeah, but anyway, yeah, actually, if we consider the kappa in the Gaussian surface, we don't consider this excess charge. Okay, this excess charge we won't consider. If you consider this Q prime, then still make it like this. Okay, still make the Gauss law like this. Okay, if you consider kappa here, then just ignore this Q prime. Okay, otherwise you will consider the same effect twice to make it wrong. So in that case, okay, it will be like you change epsilon naught to kappa epsilon naught. So the C will be like change from epsilon naught to kappa epsilon naught. Okay, and then this kappa is always larger than 1. Okay, kappa is always larger than or equal to 1. Okay, it cannot be smaller than 1. Okay, so which means that inserting the dielectric will always make the capacitance larger. Okay, so this is very important. Okay, this is very important. Actually, this is related to the speed of light in any material. Okay, yeah, because we know the speed of light in the vacuum will be the ultimate speed, okay, in the universe. Okay, that 3 times 10 to the 8th meter per second. Okay, yeah. So actually, the speed of light in other material is actually related to part of it is related to this kappa, and then also related to the magnetism characteristic. Yeah, so actually this kappa can only be 1. Okay, it will be like actually the speed of light will be like 1 over mu naught epsilon naught. Okay, later on we will talk about that more. But for other material, it would be like C equals 1 over square root of mu epsilon naught. Okay, so mu epsilon naught must be larger than or equal to mu naught epsilon naught itself. Okay, so here with a sample problem. So here it says, okay, so a parallel plate capacitor whose capacitance C equals 13.5 picofarad is charged by a battery to a potential difference. Okay, so I think I forgot to mention the SI unit is farad. Okay, the SI unit of the capacitance is farad. F-A-R-A-D. Okay, farad. So in a capital F. Okay, so it's charged by a battery to a potential difference V between these plates. The charging battery is now disconnected, and porcelain slab is slipped between the plate. What is the potential energy of the capacitor before the slab is inserted? Okay, before, okay, it is easy. So because it is nothing but Q equals sorry, not Q equals. It should be potential energy. Potential energy should be U or UI. Okay, the initial potential energy is half of CV square. Okay, because we already have C and also V. Okay, so we can plug in the numbers. Half of 13.5 times 10 to negative 12, and then times 12.5 square. Okay, so this is 1.055 times 10 to negative 9 joule. Okay, like this. So this is pretty easy. We just make use of the U equals half of CV square. Okay, so the next question is potential energy after the slab is inserted. After the slab is inserted. Okay, so after after the slab is inserted to the capacitor, so the C prime will be like kappa C, so which is nothing but 6.5 times 13.5, which is times 10 to negative 12. Okay, like this. So VF will be Q square over 2C prime. Okay, the Q doesn't change because the battery, the charging battery is now disconnected, so that we assume that no charge can go in, go out, okay, of the capacitor. Okay, so Q will be originally 13.5 times 10 to negative 12 times 12.5. Okay, so this will be the original charge, okay, taking the square. So divided by 2 times 6.5 times 13.5 times 10 to negative 12. Okay, so this one will be 1.62 times 10 to negative 10 joule. Okay, so this one is smaller than the initial. Okay, so this is 1.62 times 10 to the 10th power. This is 1.055 times 10 to the 9th power. Yeah, almost 1/9. Okay, almost 1/9. Okay, so which means that the work done, okay, the work done will be VI minus VF. Okay, negative delta U will be 1. Of course, it is not asked by this question, but actually 1.055 times 10 to negative 9 minus 1.62 times 10 to negative 10 will be 8.93 times 10 to negative 10. Okay, so which means that you actually need to do some work to insert this slab into the capacitor. So some of the energy goes in the dielectric because as I mentioned, if you have a dielectric inside the capacitor, which means that it will generate some E field, cancel some of the external E field. So there are some energy stored in the dielectric itself. Okay, so you will see like so for the capacitor itself. Okay, so you can see that, okay, the energy stored there become less. Okay, you didn't do much, you feel like, but actually you insert the step. Okay, but so that some of the energy are absorbed by that dielectric. Okay, so here we have an other sample problem to wrap up this chapter. Okay, so here we have a parallel plate capacitor. The area is capital A, and then plate separation D. Okay, so the potential difference V0 is applied between the plate. The battery is then disconnected. And the dielectric slab of thickness B and the dielectric constant kappa is placed between the plate. Assume A, D, V0, and B and kappa. Okay, with all these values. Okay, so what is the capacitance C0 before the slab is inserted? Okay, so this is pretty straightforward. You just make use of C0 is epsilon naught A over D. Okay, you have A, you have D, you have epsilon naught. Okay, so this is 8.85 times 10 to negative 12, and then times A is this one. Okay, but this is centimeter square, so it should be 115 times 10 to negative 4 to make it meter square. And then this is 1.24 centimeter, so 0.0124 meter. Okay, So this is 8.21 picofarad. 8.21 picofarad is the initial capacitance. Initial capacitance without the slab. Okay, so this is the initial one. Okay, so it asks you what free charge appears on the plate. What is the free charge on the plate? So this should be Q will be C0 V0. Okay, C0 V0. V0 we already have. C0 we already calculate. So this is 8.21 times 10 to the negative 12, and then times 85.5 volts. Okay, so the charge amount will be 7.02 times 10 to the negative 10 coulomb. Okay, so this is the charge. Okay, so far pretty straightforward. So we just make use of the C equals epsilon naught A over D, and then Q equals CV. Okay, so the more difficult part comes here. So for question C, it asks you what is the E field E0 in the gap between the plate and the dielectric slab. Okay, what it really means is that it should generate some E field, okay, E0 here, due to the the parallel plate, okay, the external E field, okay. This one also have the E0, yeah, but inside there will be some E prime, okay, or whatever you try to call it, maybe. Yeah, anyway, the E0 is the E field between the plate and the slab. Okay, so here what we try to do is try to assume the Gaussian surface. Okay, so we try to make this Gaussian surface 1. Okay, so just as what we have done before, okay, we can quickly say that, okay, only this side contribute to the surface integral, okay, because I've already repeated many times, okay, so I don't try to explain detailedly again. Okay, so what it really means is that epsilon naught integration of E dot dA equals Q. Okay, this is nothing but Q here. This is nothing but Q here. Okay, so here actually we have E0. E0 is pointing downward. So we have E0 times A, and then epsilon naught in the front, and then equals Q. Okay, something like this. So we will have E0 is actually Q0 over epsilon naught A. So which is should be Q here, which is 7.02 times 10 to negative 12. Okay, which is this one. Okay, so we don't have 0. Okay, we don't have 0 here. And then 8.85 times 10 to negative 12. And then the cross-section area 115 times 10 to negative 4th power is the cross-section area. So E0 will be 6,900 volt per meter. Okay, so this is the E field between the plate and the slab. So this is still unrelated to the slab yet. Okay, so for the fourth one, okay, for the question D, okay, it asks you what is the E field E1. Okay, so actually this is E1 rather than E prime. E1, okay, E1, okay, so I draw it again here, E0 outside and then E1 inside. Okay, so what is the E field E1 in the dielectric slab? So here, rather than using Gaussian surface 1, we try to use the Gaussian surface 2 like this. Okay, and actually what we want to find is the E1, okay, inside. Okay, so actually also only this green surface contribute to the surface integral. Okay, so this is perpendicular, this is inside the, okay, inside the conductor. Okay, so it will be 0. So actually for this one, this surface is actually inside the dielectric. So we try to use epsilon naught integration of kappa EDA, okay, equals. Here the enclosed charge is negative Q. Okay, the enclosed charge is negative Q. So this Q prime, this positive Q prime, negative Q prime doesn't count. Okay, because yeah, as I mentioned, if you consider this kappa, you don't count the Q prime again. Okay, they are the same effects. So in this case, we have a negative Q here. We have negative Q here. So only related to this this negative charge. So here we have epsilon naught. Okay, so here we have a little bit tricky things is that this E1 is pointing downward. Okay, actually canceling part of the E0, but dA is actually pointing upwards. So E1 dA actually point to opposite side. So which means that here we have negative kappa EA, E1A, okay, equals negative Q, okay, so that these two negative side cancels, okay, so we have E1 equals Q over, okay, so also Q here, so which is kappa epsilon naught A, okay, so which is 7.02 times 10 to negative 12, and then this is 2.61, and then times 8.85 times 10 to negative 12, and then 115 times 10 to negative 4, okay, like this. Okay, so finally, this is 2640 volt per meter. Okay, actually you can just pick it like 69. This is actually equal to 6900 over 2.61. Okay, if you sensitive enough, okay, you feel like okay, this one and this one is actually this one. Okay, it's just like 6,900 over 2.61 is actually this one. So finally for question E is ask you what is the potential difference V between the plate after the slab has been introduced. Okay, so here we try to do the line integral from the negative plate all the way up to the positive plate. Okay, so this is the I, this is the F. Okay, so V will be integration of negative to positive EDS. Okay, so it will be like okay, for this part, this is E0, this is also E0, and this is E1. Okay, so actually this part is B. Okay, the thickness of B. So inside the dielectric, it will be like E1 times B. And then for the outer part, okay, outside the or between the slab and the plate, okay, no matter how high it is, okay, so these two parts add up to be D minus B, okay, add up to be D minus B. We don't need to care about how high the slab is. but actually E0 times D minus B will be the total height for the gap between the slab and the parallel plate. Okay, so actually we can just plug in all the numbers. E0 is 6900. D minus B is this one and this one. Okay, so 1.24 minus 0.68 times 10 to the negative second power. And then plus E1 is this one, 2640. 2640 times 0.78 times 10 to the negative second power. So it turns out to be 52.3 volt. 52.3 volt. Okay, so originally the V is 85.5. Okay, so after inserting the slab, the V is 52.3. Not divide 55.5 by 2.61. Okay, because the slab here with a thickness B, okay, which is only part of the distance between the parallel plate, not the whole separation. Okay, so it only reduced 85.5 by 40%, around 40%. Yeah. Yeah. Okay, so finally, what is the capacitance with the slab in place between the plate of the capacitor? Okay, so what is the capacitance after inserting the slab? So finally, C is actually Q over V. Okay, so Q doesn't change. 702 times 10 to negative 12 over. Finally, V is 52.3. 52.3. So which is 13.4 picofarad. So just as the previous question, okay, it doesn't multiply C by 2.61. Okay, it only increased like also 40%. Originally C is 8.21. Okay, 8.21. Okay, C0 is 8.21 picofarad. Okay, so only increased by 40%, 40 something percent. Yeah, maybe should be more than 50% here.